Hello and welcome to Most Significant Bit, a podcast that explores the connections between engineering, technology, humanities, and the arts. I'm Jen, and today we're discussing ant colony algorithms. In this episode, I'll provide a brief overview of the history, development, and applications of ant colony algorithms. Ant colony algorithms are a category of algorithm used for finding optimal paths between points. Virtual ants explore space and leave behind pheromones to indicate promising paths to other ants. The more promising a path is, the more ants explore it and leave pheromones, and eventually, the simulated colony converges at an ideal solution. This type of algorithm is an example of biomimicry, the technique of taking inspiration from nature to design products and systems. As their name suggests, ant colony algorithms imitate the foraging behavior of ants. The original ant colony algorithm, called Ant System, was proposed by Marco Dorigo in his 1992 PhD thesis. In his thesis, he applies the algorithm to the traveling salesman problem, both to compare its performance to that of other optimization algorithms and to compare different versions of his own ant system. He also demonstrates the versatility of ant colony algorithms by applying them to three other optimization problems: the asymmetric traveling salesman problem, the quadratic assignment problem, and the job shop scheduling problem. Subsequent iterations of Dorigo's concept alter various parameters of the algorithm to produce new results. Ant colony algorithms can have different rules about which ants leave pheromone trails, when in the process they leave pheromone trails, and the strength of the pheromone trails. Some versions split the ants into groups that communicate with each other but work independently. Others divide the solution space into parts and later combine the results from each part. Since the solution spaces for many optimization problems can be represented as points on a graph, ant colony algorithms have applications in a variety of fields. Starting off with a manufacturing example, the 2024 paper titled A Novel Ant Colony Algorithm for Optimizing 3D Printing Paths by Xinghan Lin, Jigang Huang, Wuntian Shi, and Kuyo Guo outlines how ant colony algorithms can be used to improve additive manufacturing processes. Determining the most efficient path for a 3D printer's printhead improves both print times and part quality. However, the solutions generated by existing algorithms have shortcomings, especially when printing large parts. The authors of this paper propose the use of a k-means clustering algorithm in combination with an ant colony algorithm to avoid some of these shortcomings. The k-means clustering algorithm divides the solution space, which is all the points that the printhead needs to move to while printing a layer, into smaller sections that can be better handled by the ant colony algorithm, which ultimately determines the most efficient printhead motion path. Another application of ant colony algorithms is to the design of integrated circuits. In their 2025 paper, Optimization of Integrated Circuit Routing Based on Ant Colony Algorithm, Yiming Chen and Yuhan Feng explore how ant colony algorithms can be used to develop IC wire routing schemes. Efficient wiring helps IC chips perform more reliably while also using less power, having a smaller footprint, and being cheaper to produce. In this paper, solutions generated by a customized ant colony algorithm are compared to solutions generated by other algorithms on the basis of wiring length, wiring time, signal delay, and the number of line crossings. The ant colony algorithm demonstrates significant performance improvements over the two comparable algorithms discussed in the paper, making it a promising option for generating IC layouts. A third example of ant colony algorithms usage is in urban planning to create efficient transit connections between points in a city. A 2020 paper by Juan Li and Bo Wei titled Urban-Rural Bus Path Planning Based on Ant Colony Optimization Algorithm elaborates on how to tailor an ant colony algorithm for urban design and demonstrates its efficacy in this area. Unlike the traveling salesman problem, transit systems are more than just one path between a start point and an end point. They must efficiently connect many possible start and end points. In Li and Wei's algorithm, ants move between different starting and ending locations that are weighted based on the city's population distribution. An algorithm for designing transit maps must reflect the practical considerations for implementing a design as well as its efficiency. Even if an algorithm found the most efficient solution, A city wouldn't be able to use it if it conflicted with essential infrastructure or significantly impeded transit access during construction. Researchers at Zhengzhou University propose the solution of applying pheromones to existing transit paths before the algorithm is executed. This causes the ants to develop solutions with a preference for reusing existing transit infrastructure, which would avoid the issue of having to completely shut down and scrap the original transit network, and make the solution more cost-effective. I said at the beginning of this episode that ant colony algorithms find the optimal solution to whatever problem they're tasked with solving. This isn't exactly true. Ant colony algorithms can arrive at the single best solution, but like other optimization algorithms, they tend to fall short of this ideal performance when the solution space becomes very large. This is why some variations of the algorithm divide the solution space into sections. A major reason why this decline in performance occurs is combinatorial explosion. Combinatorial explosion describes the way that, as a problem becomes more complex, the number of possible solutions can become so large that comparing every option with every other option becomes impractical or even impossible, whether that be in terms of time, available computing power, or both. So, if comparing all the options to find the best one isn't feasible, how else can you approach a problem? One answer is by using heuristics, which can be described as logical shortcuts. Heuristics cannot guarantee that the single best solution will be found, but they make it possible to find reasonably good solutions to otherwise unsolvable problems. Ant colony algorithms are heuristic, which is why researchers are continuing to develop new, improved variations. Each type of ant colony algorithm seeks to improve solution quality while minimizing processing time and power. To sum up, ant colony algorithm research and development is about finding progressively better shortcuts. Today, we covered the history, development, and applications of ant colony algorithms. Ant colony algorithms are an excellent example of how biomimicry can give rise to technological advancements both in the field of manufacturing and beyond. Thanks for listening.